Last time, we saw that given a notion of forcing, the concept of forcing question, which has the following specification. So given a formula, so if it says yes, if it answers yes, then there exists an extension which forces the formula in the natural sense. And if it answers no, then there exists an extension which forces the negation of the formula. So which was being a dividing line. So the forcing question is a dividing line between the set of conditions which forces already the sigma 1 formula, the set of conditions which forces the negation of the formula, and these are the ones which are not decided yet. And so in some cases, so there are two natural definitions of forcing questions, which are the extremal positions, and which is implemented, which is the natural one for Cohen forcing, it's on this side, and for Jokic-Shor forcing, it's on this side. But of course, we could imagine a lot of variants, and we are especially interested in forcing questions which have the good definitional properties and the good combinatorial properties. Actually, we saw that so there was some correspondence between having a nice definitional property in the sense that if you decide a sigma 0,1 property, then your question is sigma 0,1. So this is sufficient to obtain cone avoidance. And then, so with a little bit of compactness, you obtain preservation of hypermunity. And we have various combinations of independent questions which yields PA avoidance or DNC avoidance. So the goal, the first goal of today is to show that not only this concept of forcing questions applies to classical computability theory, so in the standard realm, but you can also apply it in the formal setting to prove conservation theorems. So I already started talking about conservation yesterday, but I did not plan to talk about it yet, and so I didn't gather my thoughts. So let's give a little bit of a big picture for that. So the main motivation, so let's go back to our motivation of reverse mathematics as a partial realization of Hilbert's program. So the goal was to show that infinitary mathematics could be reduced to finitary means in the sense that if you prove a finitary statement using infinitary mathematics, then you can actually prove it using finitary ones. And so the goal, what we are interested in, is to identify or to axiomatize the set of first-order consequence of our second-order statements. And it is often useful not to axiomatize it from scratch, given a second-order statement, but to reduce the question from one theory to another theory, thanks to the notion of conservation. So theory T1, so we already saw the definition yesterday. Theory T1 is conservative over another theory T0 over a class of formulas gamma. If for every gamma sentence, which is already provable in T1, you can prove it over T0. And so what's the case which interests us in particular is when you consider as gamma the collection of all first-order sentences. And so if T1 is a conservative extension of T0 for the first-order sentences, then they have the same first-order part. And so the interest is to find a theory which is a reference theory for which we already know the first-order parts, and then when you analyze the theory T1, you try just to prove conservation over T0. And so for that, the simplest way to do that is through the notion of omega extension. So a second-order structure is an omega extension of another structure if the collection of integers remains the same with the same interpretation of the operations, which means that you increase only the second-order part. And it's easy to see that if every countable model of a countable theory T0 admits an omega extension into another countable theory T1, then T1 is conservative over T0 for all the first-order sentences. And so the proof is very simple. Assume that you have a first-order sentence which is not provable over T0. Then you have a countable model of T0 and the negation of this sentence. So take the omega extension of your structure which satisfies T1. And because you keep the same first-order part or the same integers, the truth value of the formula will not be changed. So it will still remain a model of non-phi 0, non-phi, and a model of T1. So it shows that T1 does not prove phi. And actually, we get, with the notion of omega extension, we get a slightly stronger property. We can show that if you have the same, this omega extension, it shows that T1 is pi11 conservative over T0, and the proof is almost the same, in the sense that if you have a pi11 sentence for which it does not hold, so which is not provable over T0, then you have a model of the negations of a sigma 1 property. And because you take an omega extension, this witnessing set will also belong to the extension, and so you will be again a model of T1 and the negation of the formula, so which shows that T1 does not prove the pi11 sentence. So we obtain something stronger. So we will actually only consider pi11 conservative statements. And so we want to reduce it to something for which we have we know well the first order part. And so there are two reference schemes of statements, which are induction and collection schemes. So I already defined them so in the last lecture, so let's not go again through it. And so we can really classify some strengths in terms of induction or equivalently in terms of collection or in terms of Least principle, with some subtleties of whether it collapses or not on the class of formulas. But we are interested in particular in this level, which is the level of RCA0. So this is the exact level of induction that is given by RCA0, which is sigma 01 induction. And this level, so for all of these statements, the first order part is well known. It's just when you remove the superscript 0, it means that it's the sentences which are first order in the sense that they are not allowed to have any occurrence of sets. They have no set parameter. And so it's easy to show that, for example, Q, so Robinson arithmetic plus I sigma 1 is in the first order part of such statements of RCA0, because if you take any model of that, actually, if you just add as a second order part the delta 01 definable sets with parameters in your first order structure, you become a model of RCA0. So it's not a complicated thing to show that. So our goal in general is, given a pi12 problem P, we want to show that RCA0 plus P is a pi11 conservative extension of RCA0. And if we have that, then we will know that the first order part of RCA0 plus P is Robinson arithmetic plus I sigma 1. Usually we also consider that Q is part of I sigma 1, and so we just say I sigma 1. So that's the goal. And the approach for that, because of this omega extension proof, is given a pi12 problem, we want to show that every countable model of RCA0 is omega extended into a model of RCA0 plus P. So then, by the previous consideration, the first order part of RCA0 plus P is again Robinson arithmetic plus I sigma 1. Okay? But so, let's just make a very small definition. Given a second order structure and a set, you can define the structure, the smallest omega extension containing all the delta 01 definable sets in the original structure and the set G. And an easy lemma from Friedman shows that if the original structure is a model of RCA0, and if when you add the set G, so every sigma 01 formula with parameters in M and having G as a parameter, if it satisfies induction, then actually the extended model satisfies RCA0. So it satisfies delta 01 comprehension by construction, because we close it under delta 01 comprehension, and it will still satisfy, as I said yesterday, sigma 01 induction, because you can translate a sigma 01 formula in the original model, in this model, as a sigma 01 formula in the original model. So, if you recall, in the first lecture, we were showing how to construct an omega model of RCA0 plus P for a pi12 problem P, starting with so we were actually doing constructing a Turing ideal by making an increasing family of Turing ideals and taking the union of all of these. Actually, to make an omega extension from RCA0 to RCA0 plus P, so the proof is almost the same. The construction is almost the same. So you start with a countable model of RCA0. And at some stage, we have some countable model of RCA0, which is actually an omega extension of M0. And you pick an instance of your problem in Mn. You choose a solution so that you still satisfy I sigma 01. So you still satisfy sigma 01 induction on this extended model. And then you define mn plus 1 to be the downward closure of this extended model with delta 01 comprehension. And then at the end, you define M to be the union of this increasing sequence of omega extensions. And we claim that if, so by default, it is already a model for RC0. And if you chose carefully the sequence of instances to consider so that each instance at some point receives attention, then it will also be a model of P. So that's the standard way of making an omega extension. And so the core point here is you want to find a solution so that it satisfies sigma 01 induction. So that's the key element in proving pi11 conservation over RC0. And so this is where we are going to use the forcing equation. We are going to see that the features of the forcing equation are helpful to preserve sigma 01 induction. So let's refine our approach and say that given a pi12 problem, we want to show that we can do one step of this construction. So we want to show that given a countable model of RC0 and given a P instance of an instance of P in M, we can find a solution so that it still it satisfies sigma 01 induction. And if we are able to do that, then we can make the previous construction and show that RC0 plus P is pi11 conservative over RC0, and then that the first order part of RC0 plus P is Robinson arithmetic and I sigma 1. Okay? And so let's exemplify this technique with Weak-Unix lemma that you all know well now. So every infinite binary tree admits an infinite path. And we want to show that Weak-Unix lemma is pi11 conservative over RC0. And so for this, all we need to show is that given a countable model of RC0 and a tree, an infinite binary tree in the second order part of the model, you can find a path so that the extended model satisfies RC0, but so which means that just M join G satisfies I sigma 1. So this is just a formalized version of the Jokushore notion of forcing. So we have set of all, so we consider all the infinite binary trees which belong to the model, and we have this forcing question for sigma 01 formulas phi, which is there some level in the tree so that everybody at this level already satisfies the formula. So here I'm being a bit clumsy. So every sigma 01 formula can be normalized so that it induces also a sigma 01 formula over the finite strings, and so that this holds if and only there is an initial segment of it for which it holds. And actually, this formula is monotonous in the sense that if it holds for sigma and tau is an extension of sigma, then it also holds for tau. So we just identify those two formulas, but this is just a small syntactic manipulation. And so it's easy to see that this specification of the specification of the forcing question holds over this formalized setting. So if it answers yes, even for formulas which have parameter in the model, then there exists an extension. So actually, then you already force the formula. And if the answer is no, then there exists an extension forcing the negation. So it's a bit stronger property than just being a forcing question, because you know that in the case yes, you already force the formula. I still already have used all the battery power of my remote. Okay, no, just the pointer, just the pointer. So what we want to show is preservation of sigma 01 induction. And so we want to show that the following density lemma holds. And if it holds, then actually we show that for this formula phi, induction holds. So you have a sigma 01 formula with parameters in M, and we want to, and if it does not hold for some B, we want to show that either it does not hold on 0, or there is some A so that it holds for A and not for A plus 1. We want to show that. And so this is, as always, a trichotomy. So given some condition T, define the sigma 01 set, so sigma 01 set with parameters in the model, so which is a set of X's so that the formula holds. And we have this case analysis saying if 0 does not belong to the set, then by definition of the forcing question, there exists an extension forcing the negation of the formula for 0. And if there is some A so that which belongs to W and A plus 1 does not, then here we are using the stronger property of this sigma 01 forcing question, saying that because A belongs to W, then the condition T already forces phi A of G, phi of A and G. And because A plus 1 does not belong to W, then there exists an extension which forces negation of phi A plus 1 of G. But because you were already forcing phi AG, then it means that the extension forces simultaneously phi AG and non-phi A plus 1G. So you manage to find an extension which simultaneously answers both questions. And in third case, you witness a failure of sigma 01 induction for the original model, which is not possible. To get a contradiction. So let's take another example, which is a beautiful theorem from Tosner, which morally says that from the viewpoint of RCA0, arbitrary sets are indistinguishable from delta 2 sets. So for any countable model of RCA0 and for any set, you can make an omega extension of your model so that this set belongs delta 2 with respect to the omega extension. Yeah, that's all. And so really it corresponds to the intuition that if you are delta 2, so you have a delta 2 approximation, you cannot exploit it at all because for finitary stuff, because it's only a limit information, and you at any finite amount of time you will never have any information about anything with respect to the delta 2 approximation. So let's try to prove this statement. If you take G equals A, then it will make, so for example, if you take A to not satisfy sigma 01 induction, then if you take G equals A, you will make fail sigma 01 induction in the extended model. Maybe I stated wrongly? No, it's not an element. It's arbitrary subset of the first order part. So for this, we are going to use a notion of forcing that I call Tosner forcing. The goal is to build directly a delta 2. So we are not going to build a set. We are going to build a stable function in the sense that we are going to build a delta 2 approximation of our sets. So it's a function with two parameters which stabilizes on every input. And for that, we are going to approximate this function of pairs as a pair G. So G is just a finite initial segment. So it's the Cohen part of it. So it's the finite initial segment of the function that we are building. And I is a finite set of locked columns. So the goal is so if we did not have I, if we just work with G, if we take a generic filter using Cohen genericity, we would have an arbitrary function of pairs. But we want the function to stabilize. And so here, I is just a finite set of saying, from now on, the columns of I are fixed and they have already reached their limit behavior. And from now on, everything you add to G for those columns have to be the right value. So you can define the denotation of a condition, Gi, to be just an arbitrary function over pairs, which contains G as an initial segment, so it's compatible with G, and for any pairs which you add to H, if it already belongs to the locked column, then it has to be the right value. So that's all we say. And so the extension is the immediate, the obvious extension. So for this, it is easy to define a sigma 01 question to be, the sigma 01 question is really similar to the question of Cohen forcing. We just ask, can I find an extension of my finite function G into a function H, finite function H, so that your formula holds. And this is really sigma 01 because, so the set A is not computable, but because the set I is finite, we just hard code a finite amount of information of the set A to ask our question. in the sense that this question is not uniform. So it's not uniformly sigma 01 in the condition, but it's if you fixed the condition, and so you hardcode the initial segment of A with the for the locked for the columns of I, these questions become sigma 01. And so it's easy to see that it behaves like co-enforcing, in the sense that if the answer is yes, then there exists an extension which forces the formula, and if the answer is no, then you already forces the negation of the formula. Very small technical points here. Because the set A is arbitrary, the set for which we want to make the delta 2 approximations, we don't have the initial segments. We don't necessarily have the initial segments of your set A in the model. So which means that here I is really finite in the sense that the size of I is a standard number. We really want to. We are really going to exploit the fact that this is a countable model, and so we can interleave steps where we increase the stem, and then at some steps we increase the size by taking another element of your countable model and fixing the column. But so which means that we are not going to fix the columns as initial segments. We are going to fix at various points of your models. Okay, so it's not uniformly stabilized. Okay. So here, Friedman was already mentioned. We want to show still the same density lemma, saying that you preserve sigma 01 induction. And the proof is always the same. So you ask, so you consider the sigma 01 set of all x's so that your formula holds. And either you find either 0 does not belong to your set W, so you can force non-phi 0G, or A belongs to W for some A and A plus 1 does not. And here we are using another aspect, another stronger property of sigma 01 induction. Before we were using the fact that if A belongs to W, then your condition already forces A. Here we use the dual version. You say that if A plus 1 does not belong to W, then your condition already forces non-phi of A plus 1 G. And so, and because A belongs to W, there exists an extension which forces phi of A G, and so you have an extension which forces both simultaneously. So either extremal version of the forcing question is sufficient to obtain what we want. Okay? And so this motivates the following definition. A forcing question is sigma 01 and pi 01 merging if for every condition and every pair of formula for which one is sigma 01 and the other, every pair of sigma 01 formula, if independently the answer for one is yes and the answer for the other is no, then you can find a compatible simultaneous answer forcing the witnessing it, so forcing the negation of one and positively the other. And this is all we needed for making the argument work. So we can prove abstractly that if you have a sigma 01 preserving forcing question which is sigma 01 and pi 01 merging, then you can prove the density. This is absolutely not the appropriate density lemma. But you can still prove exactly the same density lemma. And here you use abstractly in case 2 the fact that you are a sigma 01 pi 01 merging. Okay. And so here we really exploited, so we have exploited the fact that torsional forcing question is a bit like co-enforcing, so it's extremal on this side, and the Joker-Shor forcing question is still extremal on the other side. So we added one more element in our correspondence. If you are sigma 01 preserving and you are sigma 01 pi 01 merging, then you can preserve sigma 01 induction. And so it's very helpful for proving pi 1 conservation statement over RC0. So let's look at a higher setting. When I say higher setting, I mean higher levels of the arithmetic hierarchy. From a purely abstract viewpoint, as a framework, it's exactly the same. So the proofs are exactly the same in the sense that, for example, so recall that the forcing question is gamma preserving for a family of formulas gamma if, well, the relation has the same complexity as the formula which is questioned. we can easily show that at every level n, if your forcing question is sigma 0 n preserving, then for every non-0 to the n minus 1 computable set, and for every Turing functional, the following set is dense. So set which forces the n minus 1th iteration of your jump not to be equal to, not to compute C. And the proof is the same. You instead of having a sigma 0 1 set, you have a sigma 0 n set, because this is a sigma 0 n formula. And then you have this case analysis for cone avoidance. So either you can force to halt on a wrong value, or you can force not to halt at a good value, and otherwise you have a sigma 0 n graph of C, and this is not possible. So purely abstractly, all the previous correspondences also hold at higher levels. But the difficult thing is actually to find a notion of forcing which admits an appropriate sigma 0, an appropriate forcing question. So that's the hard part, actually. So let's first look still at our toy example, so co-enforcing. So we all know now co-enforcing. We can define easily, naturally, inductively, the forcing question for higher levels of the arithmetic hierarchy. So if you are sigma 0 1, it's still the same. You ask, is there some tau so that your formula holds? And at higher level, it's also the same, but you just define it inductively with respect to the forcing question. So you say, is there some x and some extension for which I do not force the negation of psi, so which means morally, if you do not force the negation of it, it means that there exists an extension for which it will force the formula. So it's not too difficult to see that this satisfies the specification of a forcing question. But let's just write down this definition, because this definition abstractly is the natural inductive definition of a forcing question. Let's just say that inductively, so sigma, or not sigma, an arbitrary, in an arbitrary notion of forcing, a condition asks, is there some x that phi of gx? You define it as, is there some q which extends p? Is there some x so that q does not force the negation of phi of gx? Okay, so that's the natural definition, a natural inductive definition of the forcing question. And so it's easy in this case to see that the forcing question for sigma 1 formulas is sigma 1 preserving, because so if you are your formula phi is of the form exists x followed by psi of gx, where psi is let's say pi 0 n, then you have an existential quantifier followed by, so psi being pi 0 n, the negation is sigma 0 n. And so the negation of this is pi 0 n, so you have exist followed by pi 0 n, so you are sigma 0 n plus 1. So it's just check, it works very well. So this forcing question for sigma 0 n formulas is not only sigma 0 n preserving, but you can also check that it's sigma 0 n compact, omega pi 0 n merging, and sigma n pi n merging, simply because for co-enforcing at every level, the forcing question is extremal on this side. It might not be completely obvious why it's extremal at higher levels, because here we make it inductively in function of a forcing question for which we don't have a perfect control of where it puts the divide line. But if you have an element which is in the middle, so for which is not decided, if you are in the middle, it means that so you have some p which is in the middle. It means that there exists an extension, so there is some q smaller than p, which will actually force the formula, the pi 0 n formula. And when you force it, then the forcing question has to coincide, has to give the same answer, because when you are on one of those two sides, the forcing question has no degree of freedom. It has to coincide. So you can still easily show that if you have this following definition, whatever the lower version, the lower definition of the forcing question, here, this will be extremal on this side. Okay. And so, for example, as a consequence, we can show that no sufficiently coingeneric is high, in the sense that its jump does not compute zero double, because zero double was not already delta 2. So here, what really exploited is that this natural definition yields something, has the appropriate complexity, because the partial order of co-enforcing and the extension, so the full partial order, so the domain in the order, are computable. And so if you have a notion of forcing with a computable partial order, this will have the appropriate definition, and you will have all the good properties like co-enforcing. Let's take another example for which the partial order is not anymore computable. So Joker-Shor forcing. Here, we are going to refine a little bit the notion. We used to work with infinite computable binary trees. Now, we want to work with primitive recursive binary trees. Actually, for every computable infinite binary tree, there exists a primitive recursive binary tree which has exactly the same collection of paths. So this is without loss of generality. And so the interpretation is still the same. But it's a bit easier because we don't have a uniform enumeration of all the computable binary trees, while we have an enumeration of all the computable primitive recursive binary trees. So we need to make now, to have a different behavior for the first level and for higher levels of the forcing question. So for sigma 01 formulas, we already saw a forcing question saying, is there some level in the tree so that every node at this level will satisfy your formula? So which was on the other side of the diagram. And when you look at sigma 02 and higher formulas, actually, the complexity of the formula is high enough to absorb the complexity of the partial order. So you can ask, is there an extension? So is there some S, which is an infinite primitive recursive binary tree, which is a subset of T, for which the negation holds? And if you look at the quantifiers and so on, so S being a subset of T is just pi01, and is there some S in T? So it's absorbed, and so you can see that, for example, for sigma 02 formula, this yields a sigma 02 forcing question. So we have a distinct cases, and so which means that the forcing question in general for sigma 0n formulas is sigma 0n preserving, but depending on the level, it will not have always the same combinatorial properties. So at the first level, it behaves like a Joker-Shor forcing, so because it's Joker-Shor forcing, so it's sigma 01 compact and sigma 01 and pi 01 merging because it's extremal, so as soon as you are extremal, you are sigma 01 pi 01 merging. But you are not, for example, omega pi n merging at the first level. On the higher levels, you come back to co-enforcing somehow, and so you are sigma 01 compact, omega pi n merging, and sigma n pi n merging. So if you look at the diagram, it means that at the first level, you are extremal on this side, and at higher level, you are extremal on this side. Let's make an even less trivial example with cohesiveness. So Demi already defined the notion of a cohesive set. So an infinite set is cohesive for a countable sequence of sets if you are almost included in each. So if for each of them, you are almost included in it or in the complement. And as we are going to see, cohesiveness is really about jump computation and not really about computation. But let's not go too much into this now. The standard way of building cohesive sets is through Mathias forcing. So Mathias forcing, we already saw variants of it at least. You work with an initial segment, so like co-enforcing, and an infinite reservoir from which the elements of F will be taken in the sense that any extension of this has to take the elements from X. And so the extension just means that you increase the initial segment, you decrease the reservoir, and the new elements you put from F to E have to come from X. Okay? So the notations are, well, it's the immediate one. And so this naturally produces cohesive sets, even if you restrict yourself to computable Mathias forcing, that is, to Mathias forcing for which the reservoirs are computable. So if you have a countable sequence of computable sets, even if it's not uniformly computable, if each of them is computable, then every sufficiently generic set for computable Mathias forcing produces an R-cohesive set. And it's very easy to see because given an arbitrary condition, so Fx where X is computable, and given a column of co, so Rn, either X intersection to Rn or X intersection to the complement of Rn is infinite, which means that either one of these two extensions is a valid Mathias condition and still computable because it's the intersection of two computable sets. So you can find an extension which will satisfy that from now on I will be either included in the column or in the complement of the column. And since there are countably many computable sets, you are going to be cohesive for that. So it naturally produces cohesive sets. And at the first level, so for sigma 01 formulas, the forcing question, the natural forcing question behaves well. So if you say just, is there some extension of my stem for which it holds? And here we are really exploiting the fact that X is computable. The forcing question for sigma 01 formulas is sigma 01 preserving and really behaves like co-enforcing. So sigma 01 compact, omega pi n pi 1 merging, and sigma 01 pi 01 merging. The situation becomes more complicated if you look at higher levels. So Mathias forcing and even computable Mathias forcing does not behave well. So let's just recall that a function dominates another function if it eventually pointwise dominates it. Principal function of an infinite set is the function which to n associates the nth element of the set, starting at 0. And again, the security degree is high if its jump computes 0 double. I don't assume that it's delta 2. And so there is this very famous Martin's domination theorem making a correspondence between being high and the ability to compute fast-growing functions. The degree is high if and if it computes a function dominating every computable function. And it's easy to see that if G is sufficiently generic for computable Mathias forcing, even when you restrict reservoirs to be computable, then the principal function of G, so the set which the function which to n associates the nth element of your set, will dominate every computable function. For this, just check that. So fix any total computable function and any condition. We want to find an extension which will force the principal function of your generic set to dominate F eventually. So what you just need to do is to sparsify your reservoir. So you just take a sub-reservoir so that if you take the principal function, it will grow very fast. So just take appropriate y so that P F union y dominates F, and this will force your function to dominate it. So it's really eventually dominating because of this initial segment F, which is fixed. So you cannot really force to be sparse in the initial segment, but eventually it will be sufficiently sparse. And the set Y can be taken to be computable if F is computable. So it's easy to see that it will make fast-growing functions. So really, Mathias forcing is not very good at higher levels because it produces sparse sets if you are sufficiently generic, and sparse sets, thanks to the principal function, compute fast-growing function, and then so you have too much computational power. So the idea is we must be a bit more careful and restrict the reservoirs. So given an instance of co, so a countable sequence of so we need to make a few definitions. Given an instance of co, we can define and a binary string. We can define the Boolean combination of those sets according to the binary string. And intuitively, when you want to build a cohesive set, you have to make some decisions. Am I going to, given some column, am I going to be included in it or in the complement? And so all sigmas means are some choices, are some finite amount of choices. And you can define the tree of all possible choices. So T of R is a sigma 01 tree, so that if you make this choice, you still have some amount of elements in it. So at least the kernelity of sigma. And this tree, so is such that if you are an extensible node in this tree, then R sigma is infinite. And so somehow if you have a cohesive set, then it induces an infinite binary sequence of choices, and this infinite binary sequence of choices will be a path through this tree. So this is possible choices. And so a pair, F sigma, denotes a Mathias condition of the form F is the original segment and R sigma is the reservoir for which so we have to remove we just want to make it syntactically look like a Mathias condition, so we remove finitely many elements. But so given an arbitrary sigma, it's not necessarily a Mathias condition because the reservoir might be finite. But if so, you are a true Mathias condition if and only if sigma is extensible in your tree. Okay. So now we are ready to define a more careful notion of forcing to produce cohesive sets, but with better forcing questions. So the idea is to work with still an initial segment f, which will be the set that we are going to build. And then instead of working with an arbitrary reservoir, the reservoir will be a Boolean combination of the columns that we have chosen so far. So we only need sigma then to represent the reservoir because it's just a Boolean combination. And we want that sigma is a stem. So it looks like a root of an infinite subtree of your original tree. So at first sight, it might be strange. We would have thought that working with why do we need the last parameter? It could have been sufficient to work with f sigma and asking sigma to be extensible in T of R. But we will see later how to exploit this last column. And so a condition extends another condition if the extension looks like the Mathias extension with respect to E tau and f sigma. And we are allowed to restrict this. And morally, in a Mathias condition, the reservoir forces some negative information. It prevents you from adding elements to your set. So if you have an element in your reservoir, it doesn't mean that it will necessarily belong to your set at the end. But if an element does not belong to the reservoir, we already know that it will not belong to it. So it's negative information. And T, so if you have the last component, morally, because we are going to restrict your tree, your original tree, you are going to restrict it, this will restrict the possible choices of reservoirs because you will have less and less possible sigmas. And if you restrict the reservoirs, you are going to restrict the negative information that you can force. So taking a subtree of T will force some positive information because you are going to say, from now on, I prevent you from removing too many elements from my reservoirs. So in terms of information, T will force some positive information, while the reservoir is a negative one, which is actually very useful because at the first level, Pi01 formula, you want we want to have at the second level a better notion for Pi02 statements, for example. And a Pi02 is a countable collection of sigma 01 statements. And so here, T will be a way of forcing a countable collection of sigma 1 statements simultaneously. But there is no need to fully understand that to understand what remains. So let's define, by a case analysis, a forcing question at every level of the arithmetic hierarchy for this notion of forcing. At the first level, it's like computable Mathias forcing. You just ask, is there can I extend my stem by my initial segment f by a block so that my formula holds? And it's sigma 01 because R sigma is computable. So sigma 01 question. So the forcing question for sigma 01 is sigma 01 property, is sigma 01 preserving and behaves exactly like Cohen forcing, the forcing question for Cohen genericity forcing. So you have all these properties. At the second level, actually, it will look like forcing with trees. It will look like the Joker-Shor forcing. So we have a sigma 02 formula, so exists x followed by a Pi01 formula phi. And you ask, can I find an extension? So just, first of all, okay, notice that here, the formula, the question was not depending on T, on the last component. So designing a sigma 01 or Pi01 property does not depend on the last component. And the specification of the forcing question, the extension witnessing the question, will not change this part, the last component. Here, this is a typo, so we need a last component in here. F sigma and T, when you ask the question, it means, can I find an extension of my initial segment? And is there a level in this tree, in the 0' primitive recursive tree, so that for every tau at this level, considering this as an extension, the F union E and tau, you have the negation of this formula. you can check that this actually satisfies the specification of a force equation for sigma 02 formulas, in the sense that if the answer is yes, it means that you can extend E, so you can make F union E, and among the taux which are at level L, there must be one tau which is extensible. So you take this tau, and then you take T to be the restriction of the tree below tau. So if the case is yes, you take F union E, you take tau, a tau which is of length L, which is extensible in T, and then you take T restricted to tau, which means that you take the sub-branch below it. So this is something which will force. Okay. Oh no, and inductively actually, because you have the negation, you have an extension of this. So this is a valid extension, and by induction, there exists an extension which forces phi of Gx. And if the answer is no, then it means that what we add to F, at every level of the tree, there exists a node for which it will not answer. It will answer yes, and so we can restrict our tree to those nodes witnessing it, and this will be an extension which will force our pi2 statement. So here again, a typo. So the forcing question for sigma 2 formulas is sigma 2 preserving. So we can check that this formula has the appropriate complexity. And it is so sigma 02 compact and sigma 02 and pi2 merging, but it's not omega pi2 merging because it behaves like Jokic forcing instead of the Jokic forcing is rather than the Cohen forcing. And in the higher cases, we go back to Cohen forcing, in the sense that now, as soon as you are sigma 03, you can absorb the complexity of the partial order in the formula, and so you can really ask the usual question. So, is there an extension for which I have the negation of the formula? And so, still same typo. The question, forcing question for sigma 0n formulas is sigma 0n preserving for n greater or equal to 3. And then you have the properties of Cohen forcing, so combinatorial properties of Cohen forcing. So to summarize, we have really a three-case analysis in the notion of forcing for Co. At the first level, it behaves like Cohen forcing. At the second level, it behaves like Jokic forcing. And at higher levels, it still goes back to Cohen forcing. Okay? So this is a non-trivial application of it. And so there are other possibilities of other non-trivial applications, in particular for the pigeonhole principle. So recall that at the first level, there was sigma 01 preserving forcing question for sigma 01 formulas using a disjunctive notion of forcing. And thanks to that, so Dermier and Karl managed to prove strong conavoidance of the pigeonhole principle, which means that for every non-computable set, and every two partition, you can find a solution which still does not compute the set. And this was using this disjunctive notion of forcing, where you make two, so it's a variant of mathematical forcing where you have two initial segments that you build simultaneously. And so here is the definition, but I'm not going to work with this. All I say is that it's a variant of mathematical forcing. And because of this, it does not behave well at higher levels. So you still have to change strongly, to change this notion of forcing by restricting the reservoirs. But so with enough work, we can design a notion of forcing which has the appropriate, so sigma 0n definable forcing question for sigma 0n properties. And so we can apply this framework and show that it holds at every level of the arithmetic hierarchy. But as usual, so once you have the forcing question with the good properties, it's immediate because the framework is very simple. But the very difficult part is to find an appropriate notion of forcing which has the good forcing question. And sometimes you have to define another forcing question. Sometimes you have to find another notion of forcing which has a forcing question. So you really have to work with that. Last, let's look a little bit about how to separate statements from Co. So we already saw how to separate from ACA knots, which was through cone avoidance, from weak Koenig's lemma, which was through 0-1 valued DNC avoidance, so PA avoidance somehow. We had DNC separating from DNC, which is using a DNC avoidance, so 0-1 valued, arbitrary valued DNC functions. Here we want to avoid computing solution to Co. And when I define Co, I said that it was about jump computation. So let's make this statement clear. Given a uniformly computable sequence of sets, so given a computable instance of Co, we have a correspondence between computing an R-cohesive set and computing a path through the tree of decisions. Actually, it's equivalent either to compute an infinite cohesive set or to have the jump compute a path through the tree. So in one direction, it's clear. If you have a cohesive set, then the set of decisions is delta 0-1, so it's delta 0-2, so it's easy to have the jump compute a path through T of R. And conversely, if you have a delta 2 approximation of a path, you can build a cohesive set by looking at this approximation, and you may make wrong choices at some point, but eventually you realize that you make a wrong choice and you can still go back to the other because you are never stuck. So you have an easy argument to compute a cohesive set. And also, the power of every 0' computable infinite binary tree can be represented by a computable instance of Co. In the sense that for every 0' computable infinite binary tree, there exists a computable instance of Co so that the tree of decisions coincides, or not the tree itself, but the infinite valid decisions coincide with the path of the tree. Okay? So really, the power of computing a solution to Co is the power of being able to jump compute a member of a 0' computable binary tree. So as we saw that weak Koenig's lemma had a universal instance which was represented through 0-1 valued DNC function, and this relativizes well. So a function is diagonally non-x computable if it diagonalizes with the if, so f of e diagonalizes with the if functional on input e with oracle x. And we have this correspondence of saying there exists an x computable binary tree so that the paths are exactly the x 0-1 valued DNC function, or the 0-1 valued x DNC functions. And given an x computable 0-1 valued DNC function, x DNC function, you can compute a path through any x computable infinite binary tree. And actually here, it's a non-trivial relativization because it's not only x computes a member, but it computes directly a path. Because if you have a 0-1 valued x DNC function, actually you compute x. So it's a small subtlety. But the proof is the same. And so using this, we can, and using this previous lemma, we can show that Co admits also a universal instance. So given a uniformly computable instance of given a computable instance of Co, then every set whose jump computes a 0-1 valued DNC function relative to 0' computes a cohesive set. And there exists a computable instance of Co so that the tree of decisions, so that the path, the valid decisions are exactly the 0-1 valued DNC function relative to 0', which means that so that for every solution to this instance, the jump computes a 0', 0-1 valued 0' DNC function. So this instance is a maximally complicated instance of Co. And actually, there is a very simple witness of such an instance. You just take the sequence of all primitive recursive sets. This is a maximally complicated instance of Co. But so now, we can just apply our usual framework with pi0 n merging. So recall that the function is pi0 n merging. If for every pair of sigma 1 formulas, if it answers no for both of them, then you can find a simultaneous witness of the negation of both of them. And by a simple relativization of PA avoidance, to 0 prime, or to arbitrary levels, you can have exactly the same arguments to show that you have the density lemma if you are pi 0 n merging and sigma 0 n preserving. So this is always the same. It's either I can force to halt and not be DNC relative to 0 prime, or relative to 0 to the n minus 1, or there exists some input x so that both x0 and x1 do not belong to W, in which case, by merging, I force to be diverging. And last case is I am a sigma 0 n graph of 0 prime to 0 to the n minus 1 DNC function, which is not possible. I'm going a bit fast because it's always the same arguments. It's still the framework taken abstractly. So for co-enforcing, we just having this inductive definition which has the appropriate properties, we obtain that this is not this should be relativized. Oh yeah, this should be relativized. Okay, let's conclude because so it works exactly the same way, one level up. So as a conclusion, what we want to you to recall is that if you want to understand the computability theoretic strength of a notion of forcing, the key point is to look at the combinatorial properties and the definability properties of its forcing questions. And most of these properties come from the analysis of the forcing question. You can always be reduced to that. So if you want a few references, there is this original book, which is the Bible of reverse mathematics, or at least of the early reverse mathematics by Steve Simpson, subsystem of second-order arithmetics. Then there is this nice textbook by Denis Hirschfeld, which is more computability theoretic oriented. And then there is this more recent book by Demir and Carl on reverse mathematics. And last is all this analysis in terms of forcing question is a textbook available online on my website. Okay, thank you very much for your attention.